Okay, this is Chemistry 3 specific for the HESI. So this is a direct continuation from Chemistry 2. And there's been hopefully very, very little time gap for you between 1, 2, and 3. Maybe a day or two is fine. For me, it's been a couple weeks, so I will do my best to seem cohesive with what you've already done. But I am going to draw on the knowledge you should have gained in Chemistry 1 and 2 a few times in this class, where I won't necessarily break down and completely explain what you're supposed to already know, but hopefully you've done your due diligence on those 2 classes and it'll connect the dots very easily for you. If not, if there's something I say, you know, we did this in Chem 1 or 2, and we talked a little bit about this, and it sounds totally unfamiliar, or you're having trouble completely connecting it back to the current material, then that may be an indication that you should review Chemistry 1 and 2 a bit. Definitely, as a side note, chemistry and biology, if you're doing both of those, as well as anatomy, really are classes that you probably have to go through a couple of times. So these are the types of classes that really utilize the recorded structure to let you make sure that you really get all the little details down. So like I recommend with everything, you always want to try to go from broad to specific. So you want to start with knowing the broad concepts from each of the classes. You can go through the video quickly and outline them as you're watching the video. You can write like each of the big topics down, but then not take super detailed notes and just follow along with the big concepts. And then you can go back and you can be more detailed. That is my computer, not yours. I'll fix that. So that you can be more detailed each time that you go through, picking up more info each time that you go through. So if that is something, if you're not feeling 100% on chemistry, biology, that's not surprising. It's a ton of information and there's a lot of different detail levels. So focus on the big stuff and understanding the big concepts, and then just keep moving into smaller and smaller, more detailed processes. Again, I have had a bit of a gap between teaching 1 and 2 and then now 3. So I won't be able to necessarily point out an exact location for something. And if I tried to, I might give you the wrong exact location. The concept that I just mentioned of outlining subject matter first and then coming back, I will outline this class right now so that you have an idea of what I kind of mean, and so that you have an idea of how you might be able to apply that to this class. So this might be, you might be making a decision right now that this is going to be your broad take on this class. You're going to go through this one without too much intent to try to get the details down. If so, I will go through and show you how you would find those. So the first page in this packet says states of matter. That's our first big subject area. There's several pages that are part of the states of matter concept. And then eventually you get to, well, and then there's a little bit of a, like a subtopic here. So this is still part of states of matter, but this is the phase changes. Once you've learned these, there will be a distinction in your head between just states of matter and what phase change specifically would be. So those would be 2 things we would go through in the first little part of class. Again, lots and lots of pages before you get to the next thing. The next big thing would be the properties of water. So that connects right on to the end of states of matter, but goes into more specifics about water. So that'll be our second thing. Our third thing will be energy. And that just has a little picture right now because you're going to add some stuff on there. You can add this title here if you want to do this outlining strategy. And then you'll have, I don't have titles on all of these, I apologize. So you can add them. Solutions and mixtures. This particular page, which is also then accompanied by a couple of other pages, has a few pieces of subject matter. We talk about solutions versus mixtures, and then we start into pH, although there is, pH has its own page, and that would be the next one here. My titling really fell off after the first couple of pages, so I'm glad that we decided to do this outline real quick because you would probably benefit from adding these titles. And then you'll get down here and you'll see types of chemical reactions. And again, there's a couple of pages. And then the last couple pages are balancing chemical equations. So if you did this same type of thing with Chem 1 and Chem 2, you would list out big things we talked about. So I know for a fact that Chemistry 1 started out talking about atoms, what they are, how they stack up against other states in the hierarchy of life. So how does an atom compare to a molecule versus an organ or an organ system and so on? That would be the first thing. Then we probably went into more specific properties of how they're built, how they're put together. Then we went into how they bond with one another. So that would be going on kind of into molecules and so on. I won't keep outlining that because if you don't have it in front of you, it sounds like probably a lot of gibberish. But you definitely have the capability, if you've been through these lectures once, to go back and really provide yourself an outline so that you can keep everything organized and you can remember what the big concepts are that you should know. Then you can start to work on making them more detailed. So this class will be probably easier for most of you than Chemistry 1 and 2. Those are the really intensive ones. Like I said, I will reference those two a couple of times. There's things that you have been learning that have set these subjects up to be a little bit easier. I'll mention them. I'll give a bit of a background on what we talked about, but not a ton in the interest of keeping this class from getting super long for you guys. So the first part of this is states of matter. States of matter refers to what you would think of as solids, liquids, gases. So that's familiar to everyone in some way. So when we talk about states of matter, the reason it's called that is this is when we're talking about what state something is in. Is it in its solid state? Is it in its liquid state? Or is it in a gas state? The obvious one, and the thing we're going to talk about after this section, is water. So water is the easiest to picture. It's the example that I'll be providing most of the time, and it would be most of your questions. So if you get states of matter related questions, they are probably going to be about water. So if we're talking about water, solid would be like an ice cube. Liquid would be how you would think of water, right? So liquid water in its liquid form. And then gas would be like water vapor. Another way you might picture that or think of that is like humidity. So the water that is in a gaseous form in the air around you, there definitely is water around you in the air in some capacity. If you live somewhere like I do, it's a lot. It's obvious that there's humidity. If you live somewhere super cold, in the winter at least, then you might picture how you can see your breath when it's really cold outside. Those are all examples of water vapor or of seeing water in its gas form. So these three should all sound pretty familiar, which is why water is a great example. The first thing we want to think about is what are the properties of a certain state? And so I'm going to kind of outline down here. One of the things I want to work harder on with my science classes is making sure you guys have access to somewhat of an outline so that you can see if you're replaying a video, you're watching it a second time or a third time, you're able to see where we switch from one concept to the next. So I just introduced what states of matter means, what the term means. Now we're talking about properties of states of matter. So what can you say is true about a solid, a liquid, or a gas? Then it'll be more like, how do they get there? And this is not going to be perfect. I'm just trying to give you a bit more of an outline so that as you're replaying this or as you're studying, you can see the different aspects that you need to know for states of matter. So a solid holds its shape, right? So if you switch, this whole thing is going to be kind of around the idea of having one of these things, a solid, a liquid, or a gas form of water in a container. So picture the glass that you drink out of the most often or something like that. Picture a glass, and then picture having another container. Maybe the other container is like a Tupperware. And so when we talk about these properties that we identify with these different states, what we're usually picturing is like when you switch your water, whatever form your water is in, from a container that it's currently in to another container. So under properties, you can say when you switch from one container to another. So I'm going to start sort of in the middle so that this is a little bit more obvious, and then I'll backtrack. So think of liquid. Liquid's the best example. Think of having a half glass full of water, and think of taking that half glass full of water and pouring it into a Tupperware container instead. So if you did that with a liquid, liquid is always in the shape of its container. And that doesn't sound like an obvious property until we talk about something that's not in the shape of its container, like a solid. So the reason I told you to picture a glass and then a Tupperware is when I picture a glass and a Tupperware, I kind of picture, like, we'll say this is a little Scotch glass kind of thing. And then let's say that the Tupperware looks a little bit more like this. That's why I have you thinking of two different types of containers. Is they're different sizes, they're different shapes. So if you take liquid from here to here, your liquid, I should get a blue pen for this just for the fun of it here. So if you did liquid that was like this, and I'm just going to color this in very quickly. When you poured it into here, what you would expect to happen is this, right? So it doesn't stay in the shape that it was in the other container. It takes the shape of the new container. Something you're totally aware of. You deal with this all the time. You witness this all the time, but you've probably never stopped and thought about that. So if it's liquid, it's going to take the shape of whatever container it's in, starting with the bottom of the container. It will fill across however much surface area is in the bottom of the container. Then it will begin building upward. So if you turn on the sink, you put a glass under it, the very first thing that would happen is you would get water covering just this bottom area that's kind of shaped like this. Then it would start building up in height once this whole thing was covered. In other words, the water's not going to start coming up here before it's even covered here. It's going to cover the bottom. It's almost like it does it in layers. If you switch the container that the water is in, it will be in the shape and in the size of the container. So if you have a really long, skinny container like what we just used to transfer it to, the water is going to probably look a lot different in terms of how tall it is, how much it comes up into the container, because this has a lot less surface area left to right. This is a much smaller container, so it will look much fuller. If you take the exact same amount of water and you switch it over to here, in order for it to cover this gigantic rectangular surface, it's not going to be as high up into the container. If you're confused on what I'm saying, it's because I'm not good at describing things like this. I'm not artistic. Try it. Take a little glass that's real skinny, fill it about halfway up, take something, whatever you can find that's like very wide, very rectangular, long and skinny, and switch containers, and you'll see what I mean, that the smaller something is around, the higher up the liquid comes in it. So if you take a little tiny glass, you fill it up halfway, and you pour that into a huge glass, it's not gonna look the same in the huge glass. So there's two things that we just identified. The shape of the container. So it's always going to be in the shape that the container is. So if you switch it from a rectangular shaped container to a round one, when the liquid is in a round container, it looks round. It's filling the round surface area. When it's in a rectangular one, it looks more flat and rectangular. So it's going to fill from the bottom up whatever container it has. The other thing that we just mentioned without mentioning it is fixed volume. So pouring water from one glass into another or from a glass into a Tupperware does not alter the amount of water that we have. It all adheres to itself, which we'll talk about later. Water sticks together with other water. It doesn't separate from itself. And so however much water you have, that's how much you have. So you'll see a change in the shape of the water as you change the shape of the container. If the size of the container varies a lot, you'll see that very much reflected in the shape that the water sits in, but it doesn't become more water or less water. Right now, you're probably that's kind of an abstract concept where you're like, well, of course it doesn't magically become more water. So when we talk about the state of matter that does actually alter, that will bring that back and make it make sense. So I'll loop back around then. So let's do the same thing with a solid. So you'll see the property that I just pointed out at the bottom with liquid was fixed volume. We have the same thing here with a solid, but a liquid, we say, takes the shape of its container, and a solid, we say, holds the shape. So the obvious solid is an ice cube. If you have an ice cube in your little glass and you switch that ice cube over to your Tupperware, it's still an ice cube. It's the same size it was a minute ago. It's the same shape it was a minute ago, unless it got melted somehow in that time. And so ice is completely independent of its container. An ice cube does not care what container you put it in, as long as none of the containers is hot and causes it to melt. It would just move in its exact same form because it is solid. So a solid will hold its shape and it will hold its volume. You can switch its container 10 times. It's going to look the same in each and every container. So the one that's abstract, because both of those should seem almost too obvious to where you're like, what am I missing that she's trying to get at here? Gas is where this kind of turns on its head. So you'll see that gas takes the shape of the container. So that's similar to a liquid. Liquids and gases would be seen as having the same shape as the container that they're in, whereas a solid has its own shape and it doesn't matter what container it's in. This is the part that's kind of crazy. So a gas will actually take the volume of its container. That is something we have not yet seen. Both solid and liquid say fixed volume. So when you take an ice cube and you move it around, it doesn't change in how much water is frozen into the cube or how it looks. When you move liquid around, granted, you might lose a drop of the liquid each time that you switch containers, but there's nothing magical that happens to cause there to be more water than there was before or less water than there was before. With a gas, when I say that it takes shape and volume of a container, this volume does not mean that it magically becomes more gas. Gas has a unique property where you see that liquid has what is called, and again, we'll go through this later, liquid has adhesion. All the liquid molecules hold on to each other all the time, so they always stick together. So you don't see some water hanging out up here and some over here and then some down here, because it all sticks together. Same thing with a solid for different reasons. It's all frozen together. There is no movement in this solid, and there's no movement that separates this liquid from itself. With a gas, you can see by the way that this picture is drawn, these are like individual molecules. So what's unique about a gas is a gas spreads itself out molecule by molecule. So where solids, you have chemical bonds that are holding the solid pieces together. Liquid, there's chemical bonds holding the liquid pieces together. Gas, you don't see that. You have one molecule there, one molecule there, one there, and so on. So gas is going to spread itself out molecule by molecule. It will fill its container by doing that. When I say takes the volume of the container, I mean that it fills its container, not because it magically creates more of itself. You're going to have the same number of molecules that you had before. So that's the same amount. What it does, though, is it separates them out and it takes as much space as it has. Just like a human, if you move into a much, much bigger house or apartment than you were in before, you don't live in a tiny corner of it because that's what you're used to. You spread your stuff out. So a gas and I'm going to make a little more obvious difference in our containers here. So let's say that we've got this little bitty thing. We got that. And then this was supposed to be much bigger, but I kind of have handwriting in the way. So when a gas switches containers, it's still the same amount of gas, but let's say that we have 10 molecules. I'm going to give us a number so that we can be on the exact same page that we have the exact same amount. So let's say that we have water vapor. We're still talking about water. So that's a gas form of water, and let's say there's 10 H2O molecules in this water. So if we're in this container, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's not perfect. I'm not an artist, but what I'm trying to show you is they distribute themselves evenly where each of them has as much space around it as possible. Same 10 molecules here, they're going to have a lot of space. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So same number of molecules, but it's filling its container because it's spreading across more space. There's more space in between each of the individual molecules. I will stress again, my drawings are not good for this. There is not a difference in how much space is between each molecule. So gas has a property where it can essentially spread itself out perfectly even within a container, and all of them are the same distance apart. You're not seeing that with my drawing because I'm not that symmetrical in how I think or move my pen. And then again, here's another even bigger container. And again, excuse the fact I don't have them even. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So again, all three of these, the container looks full. So the container on each of these is full. We can't say that that would happen with solid unless you had enough ice to fill an entire container up and then put it in the same sized container. Same thing with liquid. So if you moved liquid in these same three containers, you'd have a lot of liquid in this initial one because it's a teeny tiny little square one. So you'd go from looking like this to more or less kind of looking like this. Same amount, but it's going to take up a lot less space in the container relative to the size. And then this one, it would probably just kind of barely cover the bottom surface and wouldn't really be growing up from there. So that's your properties. What are the properties of a solid, a liquid, and a gas? You need to be able to recite those in a lot of different ways. So they could say which of the following correctly lists the properties of a solid, and they could have a whole bunch of things to where you could say, oh, it holds shape and it holds volume. That would be the straightforward version, right? So the straightforward question is, what properties does a solid have? What properties does a gas have? I'll give you a couple of examples of the more abstract questions. And so what I encourage is for you to really make sure that you are deeply understanding why the properties are what they are, why we're describing them the way that they are. In particular, understanding what it means and how it works to take the volume of a container. So if they asked you like, which state of matter, and I'm going to write this one down because this is a very common question. You very well might see this. The state of matter that fills, and we'll say a small container and a large. They might just say two different sized containers. Now they will actually say without altering its volume. So you have to be really careful with that word volume because that word has a double meaning. Volume refers in one sense to how much of it there is. You're not creating more gas. So if they say it this way, where they say which state of matter could fill two different sized containers, you would know that that's gas because only gas spreads to fill two different sized containers. But they actually might kind of be tricky by saying without altering its volume. What they mean is without altering how much gas there is. What you're thinking of is how the gas spreads itself. So you want to be looking for the kind of the idea of filling a container so that you're not misusing the word volume in the way that you're thinking. They could very well ask you what properties each one of these has. They could very well ask you what differences might exist from one to the other. And then they could very well ask you which state of matter would do this and that, which state of matter would do this and that. The way they would describe gas would have something to do with filling two different containers. The way that they would describe liquid could have to do with a couple of things. It would take the shape of its container, and it would take the volume of its container. They could also say that the shape is free, because there's really two words that they use to describe this. There's free and there's fixed. So fixed would mean it's not altered in any way, shape, or form. Free would mean that it can freely move. And then a solid would be when you're looking for something that nothing about it changes when you go from one container to another. So let's read through this bottom part of these notes, which recaps this in a less visual way. Make sure we didn't miss anything. So states of matter are referred to in terms of volume and shape. Remember that the word volume can be used a couple of different ways. That shouldn't scare you or overwhelm you as you're hearing that from me right now, because you're going to know what they mean because you took the time to really understand both technically and visually what's happening in this scenario. So if they're using volume as in to describe how much gas, how many molecules there actually are, you know that that's not the same as referring to the volume of the container, meaning that it is spread out within the container. Solids have fixed everything. There is nothing about a solid that's going to have the word free or that's going to say it takes the shape of something. Solids are fixed in every way. A solid doesn't care whether it's in a container, whether it's in one container versus another, it's going to be unaltered. Liquids have a fixed volume. You don't end up with it spread further. You just have it in a different shape. And changing shape is another way to refer to that. I always try, you've probably noticed by now because you're pretty close to the end of your program, I try to say things in all the ways that you might see them throughout my notes. So when you see a term that seems like it just changed from a term before, but seems to be the same concept, I'm just giving you another word for it. So there's three ways that you can say that liquid takes the shape of its container. You can say it takes shape of container or shape of container. You can say it has a changing shape, or you can say it has a free shape. So all those things would mean the same thing. And again, you should visually understand this and be able to picture it so that it really doesn't matter how they say it. It makes sense to you in context. The word changing probably did not have to be in these notes if you are working to have the visual understanding of changing something from one container to the other. You know that if it's a different shape of container, it is going to be a different shape that you're going to see the liquid in. Gases will have a changing volume in the sense of spreading out, and they will have a changing shape because the molecules are going to spread out not only to fill the size of the container, but also to fill the shape of the container. So if you had a round container versus a square container, you would see the difference in gas molecules reflected in that. So if this is the same, I'm not doing the number the same, but assume that I am. So if you get rid of that, you get rid of that. Those are in different shapes because they were taking the shape of their container. And again, changing or free would be another way to say that. Other physical properties that apply to states of matter, you don't need to sit and memorize all of these or anything like that. But again, these are all things to think about now, because if you think about them now, they'll make a lot of sense. You won't have issues when things are said differently or asked differently on the test because you will have already thought through all this. So this is not things I want you to memorize, especially this page. These are things I want you to picture right now, developing an understanding of, and add to the visuals that you just did on the last page. So the properties that are on this page are density, compressibility, and then molecular motion. So density refers to how tightly packed molecules are. Hopefully already when I said that, you pictured solid would be extremely high density, right? 100% density. There's no movement within a solid between molecules. Liquid has very high density as well because, again, there's no space anywhere, but certainly not as tightly packed. as they are in a solid. So again, we're looking at the individual molecules. Remember that up here, the only place we actually see molecules in that usage of the word is in this container here. These still have molecules, just like the gas, but they are very strongly bonded to each other on all sides. These look a little bit more free and open, but again, they are bonded together. So every one of these has molecules. They look the same. The difference is, do they sit right next to each other and are they connected to each other on all sides? Do they sit next to each other, but they can connect and disconnect themselves, which is what water can do, or are they spread out in the first place like that? So gas obviously would be low density because not only are the molecules not tightly packed, they're not even in contact with each other. So the difference in these three, solid is 100% density. So not only are the molecules connected to each other, they're connected on every side. I'm going to do my best to make a decent picture of this. So a solid would look like this. They are connected on every side. There's no space. There's no movement. A liquid is a little more, as you'll see coming up soon, it's a little more like this. These are the actual molecules that make up a liquid. They're connected to each other, but they're not like pushed up against each other, connected on all sides. That is still referred to as high density because density is how close and how tight are the molecules. In both a solid and a liquid, the molecules are up against each other, bonded to each other. That would be high density. But at the same time, even though these two say the exact same thing, you have enough knowledge about this now to know that those are both high density, but solid is the highest. And then liquid would be a little less dense. Compressibility, in my way of thinking of it, is the opposite of density. Compressibility is how much can you compress a substance down. So if you shrink from a huge container to a tiny one, how much can you compact what was in the big container to get it to fit in the little container? Again, hopefully you've got a mental image of a gas right now, because you can take a gas from being this far spread apart to being this far spread apart, and you could pretty much alter it to any container that you wanted to. Gas could switch containers within almost no limitation. If it has high density, it would by default have low compressibility. Again, you should be picturing all of these things. They should make sense to where you don't have to come back and memorize them. Density would refer to how tight the molecules are together. So if compressibility refers to how much you can move the molecules and how much you can bring them closer to each other, and if that definition helps you, add that in here. So I'm going to say, how much can you bring molecules closer to each other? Well, in a solid, they are as close as they could possibly be, so you can't bring them any closer. In a liquid, it says slightly here because there are extra chemical bonds that could happen that brought them a little bit closer, not much. So they're already up against each other, but you can compress them a little closer. And hopefully this example doesn't make it more confusing. The reason I don't draw a lot of the time is it can make it more confusing. So if these two are connected like that, I could also bring this over and I could connect it with that. And I don't expect you to understand exactly what I'm saying, but the result would be that these would be closer together. So you can compress liquid a bit, not much. If you're switching from a container this size to a container this size, and this one was almost full of water, needless to say, you're not going to get most of that water in here. But you can compress it just a hair where you get a few extra molecules squeezed in versus having no leeway at all. If you have an ice cube in this container, you can't even put it into this container because literally the cube is bigger than the container and it cannot get any smaller. So you can slightly squeeze water. Oops, I almost forgot my keyword here. You can slightly squeeze water. You can fit a few more molecules when you switch containers, not a whole lot. And then, of course, the first thing you probably thought of when we talked about the definition is gas would be highly compressible. The more space you have to begin with, the more space you can close. You can compress gas pretty much from any container to any container. So, as a very quick recap, you have some differences in how these are written. And hopefully you're able now with your mental images to see why these have simple answers, but they also have more complicated ones. Liquid and solid are both high density because density is the molecules being together. However, when you bring in compressibility to it, solids are going to be completely incompressible. You can't change a thing about them. Liquids are going to be slightly compressible, and that's going to be because they are slightly lower in density. Not low enough for me to have said medium. Liquid would not be considered a medium density. It is definitely high density. It's just a little less than a solid. The last piece of this is molecular motion. Molecular motion is crucial. It's something you'd never think about or picture when you're doing this. So molecular motion is the way molecules move and the way they interact with one another. Speed is our most common discussion point when it comes to this. What is the speed of the molecules? And again, how freely can they move around? How do they interact with each other? So in a solid, molecules can only vibrate within fixed positions. That's not like a relevant thing. You wouldn't vibrate a solid. That's just to kind of point out that they can only be moved if it's a vibration where they're all vibrated together. In a liquid, molecules move past each other both freely and rapidly. So liquids are linked to each other at one point, and there's a possible 3 points that they could be linked. So they're holding, it's like holding hands with the kid versus actually holding them up with both your arms locked around them where they can't move. So in a liquid, there's a lot of freedom in movement. So if you take the density concept and you say there has to be physical contact between one molecule and the other, that would be like a parent holding their kid's hand because they are in contact. They do have control of where that kid can go, but the kid can walk almost all the way around them. They can fall back a little. They can walk ahead a little bit because they're not locked in on all sides. The kid being locked in on all sides would be more like if you're holding them and you've got a pretty tight grip on them where they can't really lean back. They can't really lean to the side. They certainly can't get down. There's a big difference in those two ways of connecting yourself to your child. Gas, again, needless to say, very free motion. So if the molecules are very spread out, they have a lot of freedom. They can move around each other a lot. And again, rapid. So rapid motion would apply to liquid and gas. So there's similarities and differences in each of these, and they make sense when you consider the property and you consider it in the most visual way that you possibly can. Once you've got experience with that, with picturing that, then it becomes a lot easier to point out what properties would or would not be and where they line up with each other. Again, don't memorize this page, just have an understanding of it. If you understood or are working on understanding everything from the first and second page, you'll be in a very good position to where it doesn't exactly matter how they phrase something when you're answering these questions because you'll be able to just adapt your understanding. This part right here is just common TEAS descriptions. So, and really for HESI, it's the same. This particular note page originally came from TEAS. The bottom line is you need to be versatile, and I've pointed this out a million times. You're probably sick of hearing it, in how you think. So you can't have a word memorized. You can't have a description memorized because the questions are going to have all different kinds of wordings to try to throw you off. So there's no way to one-dimensionally study for the HESI. You've got to have a three-dimensional image where you can actually picture this so that if there's brand new language that you've never even seen before, you can read the language, create a mental image of what the language is describing, and then that will probably light bulb because that will be just like the mental image you already have. That said, as much as I know that you guys have the tools to adapt your thought processes right and left at any turn, I try to mention anything that I know you could see description-wise to elaborate on your thought processes now. The more things you've considered now, the more ways you've thought of something or said something now, the better. But don't memorize these because it will do you no good other than probably adding quite a bit of stress. You just need to have mental images and understandings that go with them. If you understand why gas looks and moves and works and changes containers the way it does, then if they said this, you would be able to picture a gas. So this might be a good way actually to kind of test yourself. Read each of these somehow without this, and make sure that what you picture when you see it is the state of matter you should picture. So when I say widely separated, random pattern, constant rapid motion, these are all things we described gases as having. Closely packed in a random pattern with constant rapid motion, this is the giveaway that it's liquid. And then closely packed in a regular pattern, that's the other clue of a liquid, is random versus regular. With vibrational motion. Certainly if you see anything that mentions vibrational motion, they're definitely talking about a solid. There's nothing else they describe that way within the scope of what you're doing. This last note on here is actually important also right here. When something is referred to as crystalline, that can really throw you off. That is a solid structure. So where that comes from is when you think of something like sugar or salt. If sugar is in water or some other solution, it's usually dissolved. So it's not in the crystals that you picture sugar being in. So when they say crystalline, I always picture sugar as soon as I see that word. That's what you should picture because it's a solid form. So they could ask you any of the questions we've covered so far or any of them that are coming up and use this word instead of using the word solid. That would be one of the ones that's not so terribly obvious when you run into it. So know that now so that, again, you have a mental image. When you hear crystalline, you'll picture sugar crystals and you'll know that you're talking about the solid form. Next segment is phase changes. So this is still part of states of matter, but it's definitely its own big thing to tackle. Phase changes are when something changes from solid to liquid, liquid to gas, gas to liquid, so on and so forth. So it's the transition of a substance from one of the states that you now know so much about to one of the other states. A few key kind of phrases that are important: melting point, boiling point, freezing point. If you haven't thought too much about it yet, you're about to start really thinking about it. One of the biggest, most key things that makes the difference between a solid, a liquid, and a gas. Think of water. We've been thinking of water as our example. Why would water be solid? Because it's frozen, right? Why would water be gas? Because it's hotter than what allows it to stay in a liquid form. So the solid one is obvious. The gas one is a little less obvious, but you're definitely looking at an increase in temperature each time that you move from left to right on that first picture, from solid to liquid, liquid to gas. That is increasing temperature. Melting point, of course, would be the solid turning to a gas. That would be the ice melting. Boiling point would be the point at which a liquid turns to a gas. That's boiling. Boiling point is 100 degrees Celsius. These are always going to be referred to as Celsius. And then a melting point would be above 0 degrees Celsius. So to be very clear, if something is at 0 Celsius, it is frozen. It has to go above that in order to be melting. The reason I don't just say 1 degree Celsius is it could be 0.00005 and it would still begin to melt, just probably so slowly you wouldn't be able to tell. Freezing point, of course, is liquid turning to a solid, and that's going to be at or below 0 degrees Celsius. So compare that one with that one. Make sure you're on the appropriate page as far as how you would use those wordings. They may not say above 0. They may not say at or below 0. Just know that 0 degrees Celsius is the freezing point. So anything that is at that temperature or is below that temperature is frozen. And of course, these numbers only correspond to water. So if you switched from water to ammonia or olive oil or something like that, these numbers would change. So these are the numbers for how water freezes, how water melts, and so on. You would have to be literally above that 0 to start to see melting. Needless to say, the further above that 0 you are, the faster it's going to melt. So if you're at 100 degrees, you're most certainly melted. You'd melt almost instantly, and then you'd begin turning to a gas. So just know what these numbers are and how they work. And then that sets you up for the most advanced questions. Knowing the numbers will not be necessary on a lot of the possible questions. If you do know them, that will help you if you get the worst ones. Phase changes cannot normally occur without passing through the middle liquid stage. So if you think about that, have you ever seen an ice cube turn into water vapor? No, probably not. It can happen. And that's where right here it says, however, rarely and under dynamic circumstances, a phase change may pass over the liquid phase. In any normal circumstance, a solid would become a liquid, then it would become a gas. You could have it at a really high temperature, and that could all happen very quickly, but you would most definitely hit that liquid format before you went on to the gas format. All you need to know about these rare and dynamic circumstances is what they're called. This is one of the few things you do need to have basically just memorized. I'll tell you an easy way to remember them. Sublimation is a change directly from a solid to a gas. So that would be like dry ice is a good example. Dry ice goes from frozen to water vapor because it is changing under such a dynamic circumstance that it's able to skip the requirements of a liquid. There's an old concept from probably elementary school that you might remember called alliteration, where something starts with the same letter again and again. So I kind of use alliteration to remember sublimation because sublimation starts as a solid. So starts with an S, starts as a solid, which starts with an S. If you remember that sublimation starts as a solid and that that's from solid to gas, then you're going to automatically know that the other term is gas to solid, and that is deposition. Deposition would be something that would happen only in the craziest of environments, like Mount Everest is an example. People who are climbing Mount Everest will have water vapor that's coming from their exhaling, from their breathing out, literally freeze before it actually becomes liquid. So that would be deposition. You just need to know these terms, and that is it. Next page is phase change results. So what is it called when we go from a certain phase to a certain other phase? How does it work? What's required? That sort of thing. This is the next big subtopic. So there's 3 phase change types. They'll all sound familiar to you. There's condensation, and then there is evaporation and vaporization. So those are kind of the 3. All 3 of those probably sound familiar. You probably don't feel super familiar with any of them to where you could describe it. That's where you need to be. So to change from a gas to a liquid is condensation. So how would we get from being in a gas form to being in a liquid form? The temperature would have to decrease, right? So the hottest, so if we're thinking about water, and we've got gas, liquid, solid, The hottest form of water is gas. The coldest form of water is solid. So if we're going from here to here, we are decreasing in temperature. If we're going that way, we would be increasing. So to go from a gas to a liquid, temperature has to decrease. That will cause molecules to move more slowly, because just like I just said, gas is the hottest, solid is the coldest. Solid has the slowest molecule movement, or no molecule movement. Gas has the fastest molecule movement. In other words, temperature and molecule speed go hand in hand. They are not necessarily one and the same, but they are they have causation. One causes the other. So the fastest moving molecule and the hottest molecule would need those two properties to both decrease to become liquid. So temperature decreases as a result of that. The molecules slow down. And then there is one other crucial thing, and that's this last thing here. Cohesive forces like hydrogen bonding pull molecules together. What the biggest key difference between liquids and gases is that in a gas, the molecules are literally by themselves. Even if you decrease the temperature a whole ton, way down underneath the mark that you need to hit to become liquid, that would not in and of itself do that. Just slowing the molecules down and cooling them off does not cause a liquid. It causes a gas that's much closer compounded like this, but one more step has to happen for it to actually take that liquid property, which is that the molecules have to grab onto each other. The big key difference between solids and liquids versus gases is the molecules having chemical bonds with one another. We will talk about this more in a moment. So temperature decreasing and molecules slowing down, that shouldn't feel like two things you have to memorize, just one. And then cohesive forces, specifically hydrogen bonding, have to pull the molecules together to get the final liquid property. Examples of condensation. Clouds are a visible display of condensation. So water evaporates from the surface of the earth and then eventually reaches an altitude that's colder. And so when it reaches that altitude that is colder, it will have decreased temperature, decreased molecule speed, and it becomes a liquid in the air. So the molecules are coming up off the surface of Earth. They're going up and up and up and up and up. You run into a temperature barrier at some point where suddenly it is much colder. And once they pass the temperature barrier, they're slowing down, they're cooling down, and then eventually they'll grab onto each other, which is that final thing that has to happen for a liquid form to take place. Another example of condensation, and there's tons and tons of others. So when you have a water bottle in a hot car, during the time that it's hot, you don't notice anything. It just looks normal. So water evaporates if it's hot, becomes a gas. If you have a bottle of water that's, let's say, this amount full, then as the temperature is rising, you're going to have individual molecules changing into gas and coming up into this space. When it cools back down, then these are going to change back to liquid, but they're most likely going to stick to the sides and the top, and that's where you see condensation. You can see it in this picture. That's what it looks like. That's what causes that. The other example is a drink sweating is the same thing except on the opposite side of the container. So when a drink sweats, that's because the drink is cold, and then the water vapor that's in the air is warm. If it gets a certain amount too close, it's going to turn to a liquid because it gets too cold. So all of these will be gas. They'll be unaffected. The only gas molecules that are in the air that are affected by a cold drink are the ones that get right in the proximity of the cold drink. That is why places with more humidity have more issues with a drink sweating. So I used to live in Colorado, and it's not very humid in Colorado. When I moved to Texas, I instantly noticed that whenever I had like an iced coffee or an iced drink, it would immediately seem like it just got drenched, to the point that I would take a paper towel with me to wrap my cup in the paper towel because it just got soaked the second that I walked out the door with it. That is because the more water molecules there are, the more are going to come into the proximity of the drink, the more sweat you're going to have. So if one environment looks like this and one looks like that, you're going to have more condensation here, but you're going to have it in either. All it is a matter of time for a water molecule to float too close to the side of the cup. Then it becomes a liquid, and instead of falling to the ground, although some of them do, it will stick to the side of the cup. That is, again, from properties of water. So a lot of this will be tied down when we get there. Sweating is also an example of condensation. So water secretes to the skin surface in a gas form, and then that releases heat. When it releases heat, then it becomes a liquid. Then it becomes sweat as we know it. There's two different ways that sweating works, and you have to be really careful about this with the way that the HESI questions are written. There is the condensation aspect, where inside the body you have water that's warm, extremely warm, because your body temperature is above the liquid temperature. So when that comes out through your skin, it is in a gas form. Once that comes to the surface of the skin, then all of a sudden the environment around is warmer than the environment on the skin. Then it's going to evaporate. So a good way of thinking of this, and again, just like with everything in this class, it's going to be obvious because you've done all this work right now today to make sure you can picture all of this, to make sure you understand why sweating has a couple of different elements to it, all of that. That how they word it will make it clear whether they are speaking to the condensation part of it or whether they are speaking to the evaporation part of it. So condensation, then evaporation. This having one phase change and then another is something we already saw as well. We saw it in the opposite order. So clouds, the first thing that happens for a cloud is evaporation. Then condensation. So that's the opposite. Clouds and sweat are opposite. Clouds require evaporation first, then they eventually reach an altitude where they condense. Sweating is condensation first, then evaporation. The last example of condensation is dew. Hopefully you've heard of dew. Some people have not if you don't live in the right area. Dew is like when you go out in the morning, particularly in cold environments like in the fall, somewhere like Colorado or New York, you walk outside and the grass is wet and you're absolutely certain it did not rain. The sprinklers did not come on. There's no way for the grass to be wet. That's dew. Dew is caused by the temperature dropping to a certain point where the gas vapor of water in the air can't stay gas anymore. It has to become a liquid because it's too cold, and it'll stick to leaves, it'll stick to the grass, and so on. Dew on a leaf is currently one of their favorite states of matter questions. It could also be on grass or pretty much anything. If they're describing an outside environment with a temperature drop and water suddenly appears when there doesn't seem to be a place that water came from, then you're talking about dew and you're talking about condensation. Vaporization and evaporation are very similar. And there's a lot of technicalities that I'm not going to go into here because I want you to think of this in a very polar, black and white kind of way because it will be easiest with the questions you're going to get asked. So if you've ever learned a lot about this and you know that there's some connections that I'm leaving out, don't worry about it. It's because it's beyond the level that you need. So vaporization, very importantly, is a chemical change. Evaporation is physical. Condensation, also physical. So vaporization being a chemical change makes it unique from all other phase changes. A chemical change is not reversible. Now, this is kind of an abstract concept because you've probably never thought of water this way. You've probably never thought of water not being able to go into one of its other phases, because the way we think of water, the way we interact with it, it can freely move between solid, liquid, and gas and back and forth. That's actually not true if you boil the water. If you boil water, it actually permanently breaks the hydrogen bonds. And I'm about to go into the hydrogen bonds part of it because that goes with a couple of these things. Remember what I mentioned about hydrogen bonds. Remember that I mentioned that a little bit ago when I said there's one thing that has to happen besides the temperature decreasing and the molecules slowing down. So if those two things happen, a gas does not become a liquid. It almost does. It has everything in the works to become a liquid, but the hydrogen bonds between molecules have to be there for it to become a liquid, regardless of temperature. So hydrogen bonds are what hold an H2O to another H2O. They are what make up liquid or solid forms of H2O, because those require not just an H2O molecule, but a bunch of them connected with each other. Boiling permanently breaks those. So boiling turns a liquid to a gas, right? So when you boil water, there's all that vapor that comes out of the top of it. Those vapors that are coming out of the top of your boiling pan can actually never become liquid again. And that's because they permanently lose their capability to hydrogen bond. That is irreversible. That is what vaporization is. So there's only one way that vaporization happens, and that's boiling. So it has to be at or above the boiling point for this to happen. It's a chemical change because the steam that's coming out of the top of the pan, if you were able to capture that and cool it back down, it actually would not turn back to liquid at all. It would stay as vapor. And so just to avoid confusion, there's a lot of different parts of the pan, right? So when you boil water, there's like, here's a pan, here's my little pan. There's the water itself, right? And then there's steam that's coming out of it like this, that's exiting the sides of the pan, breaking through the lid. If you leave it too long, it'll start to rattle the lid because it's trying to get out. If the pan has a lid right here, if you're picturing water drops that end up on the top of the lid, that's not molecules that got vaporized. So when you boil water, you don't boil all of it away, right? You don't let all of it vaporize. You just hit a certain temperature point. A lot of it will vaporize. There is less water in the pan after it boils than before because a lot of it's lost in the steam vapor, but you don't vaporize all of it or you wouldn't have your water still. So anything that is at or below the lid, anything that remains in the pan got changed to a gas and back to a liquid, but it did not get vaporized. Vaporization only happened for some of it. It happened for the stuff that you see coming out the top of the pan. And you'll have to take my word for it because it's a dangerous experiment to do. But if you were to capture that extremely hot steam and put it in a container and cool it down, it would not remain steam, but it also would not become liquid. So that would be vaporization. Vaporization questions are pretty straightforward. Again, I always emphasize my students understanding why and what it looks like when these things happen. Now that you've done that, the questions will be simple. It'll be vaporization being a chemical change, vaporization being a chemical change from liquid to gas, the requirement of being at or above boiling point for vaporization to happen, things along those lines. So it'll just be that you know about those properties and you can point them out when asked. You won't get anything more complicated than that. It won't even ask you why it's a chemical change. They won't ask you to describe the breaking of the bond potential. They won't have anything that in depth. I give you that so that you know it, understand it, can picture it, and then forever, hopefully, you'll never mix it up with evaporation again from that point. Evaporation is a physical change. Now we know that a physical change is not only can it change from one phase to the other, but it can go back the same way that it came. So if water evaporates into gas, all that has to happen is it has to cool back down. The molecules would in turn slow back down, and then hydrogen bonds would be able to take place, and it would be a liquid again. So with this, temperature increases, speed of molecules increases. This is the opposite of condensation, because this is to go from liquid to gas instead of gas to liquid. Evaporation, the biggest, most widespread example is the oceans and lakes and rivers are constantly evaporating water into the atmosphere, which eventually condenses back into clouds and eventually rains to bring it back to the environment. So that's an evaporation and condensation cycle. If you leave a glass of water on your nightstand for several days, especially if it's pretty warm in the house, that would evaporate. So eventually the glass of water would no longer have water in it. That would take a while. Those would be examples of evaporation. So you want a very different mental image of vaporization than you have of evaporation. And then categories of reactions will be fairly obvious now. All of these different phase changes between these three different phases, they all relate to one particular thing. Either heat is going in or heat is coming out. So again, I'll put my solid, liquid, gas. We talked about the fact that if you're moving this way, your temp is increasing, and in turn, your molecule speed is increasing. If you're moving this way, it's decreasing, both of those things. When you think about that from a category standpoint, you could either say it's endothermic or it's exothermic. Endo is to put heat in. You know that endo always means in. So an endothermic reaction would require heat being put into the substance. Which direction would that go? So would endothermic take us from solid to liquid, liquid to gas? Or would endothermic take us from gas to liquid, liquid to solid? So the answer to that is endothermic, putting heat in, would move us from solid to liquid and from liquid to gas. Exothermic is heat releasing. There's only one example of that, and that's condensation. Well, and freezing. You're not going to get asked about freezing as a phase change, but those are the two. So exothermic releases heat. You want to think about which phase you're starting with and which phase you're ending with, and that would tell you whether the heat increased in the substance or decreased. If it decreased, that's exothermic. That'll bring you this direction. If it's increased, it's endothermic, and that'll bring you that direction. This little thing at the bottom of this page, which I'm about to elaborate on, in green, it says the difference between liquid and gas phases is intermolecular forces like hydrogen bonds. These pull molecules together, making them exist as a liquid molecule. I'm going to try really hard not to end up on a rant here, because I rant about this every time I try to lecture it. I have alluded to it. The one thing I want you to capture more than anything else, hence not wanting to wind up in my rant, is I want you to be thinking about this from a non-chemistry standpoint. So I want you to think of what I've said a couple times already. When you go from gas to liquid, so here we are at a gas, here we are at a liquid, not only does temperature have to decrease and then molecule speed have to decrease, but they also have to grab each other. Molecules have to grab each other. So that's kind of an abstract concept, even with all the mental images you've been working on developing. But essentially what I would tell you to picture is, here's a gas, here's 5 gas molecules, here's a liquid, we'll say this is 5 liquid molecules. So if temperature decreases and molecule speed decreases, you would not look like this anymore. you would look a lot more like this. The molecules would be very, very close together because they need heat and they need molecule speed to be able to spread themselves out into the container the way that we picture them being. The last final thing for it to actually identify as a liquid, for it to actually look like a liquid, is it's going to have to be able to bond molecule to molecule. One of the properties of water is that there's multiple molecules of H2O held together by hydrogen bonds. This ties back to something we talked about much earlier in chemistry, couldn't tell you exactly where. There's two types of chemical bond. The one we've really focused on is the ionic and covalent bonds. That's what we spent a lot of class time talking about. Those are in a category together. Let me see if I have I don't really have a page that's blanker than this, so I'm going to write it over this. You should definitely do this on another piece of paper, though, so that it's not on top of your questions. So there's two categories by which bonding happens. One of them is intramolecular. The other is inter. Hopefully you have been working on your vocab and spelling and all that good stuff to where you remember that these are prefixes you're supposed to know the definition for. That will most certainly help you make sure you have all the knowledge that you need to have. Intra means within, and inter means between. And by itself, that's not a super obvious difference. It's harder in English to define this than it is in science. So you can use this now, scientific side of it, to make it a little bit easier on yourself. So within, in a science context, these are going to be your covalent and your ionic bonds. What covalent and ionic bonds do is they bring one atom to another atom. So they attach an atom to another atom. Sorry, that's kind of hard to see. And what happens is it makes a molecule. So if you just have carbon by itself, you don't have a molecule, you have an atom. If you have C2, carbon 2, or you have CO2, this is now a molecule. The way that the O got involved or the way that the C attached to the other C is either by covalent or ionic bonds. So the way that this relates to water, as you know, water is H2O. That is two hydrogens and an oxygen. You do not have water if you don't have those three things already bonded. H2O is held together by a covalent bond. We'll be talking about that shortly. But to even be considering that we have water in front of us, that already has to be that way. We don't consider having an H that's over here and then another H there and an O there. That's not water. Those are atoms of hydrogen and atoms of oxygen. So when we are talking about phase changes, the very first thing that I said to you today is we're going to picture water. We're going to talk about water. We are absolutely assuming that this covalent bond happened a long time ago and remains in place now. So the difference between a solid and a liquid form of water, it's still water, right? We're still talking about water. An ice cube, a glass of water, and water vapor, those are all water. So H2O already has to be covalently bonded long before we have this discussion. If you're answering other chemistry questions, you're going to be answering questions like that. So intramolecular would be all the questions that we've discussed in the past. How would you know how to show the bond between sodium and chlorine that creates NaCl, table salt? All of that has to do with intramolecular. When you're in phase changes, so just be aware when a question that's in front of you is a phase change question, it is assumed that we already have H2O. Or if they happen to ask about this and not be talking about water, it's almost always water they're talking about. You're going to assume that whatever molecules are required were made a long time ago and they're in place and we already have H2O. So an intermolecular, and inter means between, this is going to hold a whole molecule to another whole molecule. There's a huge difference. I know you're not chemistry people, and I don't blame you at all because neither am I. But you have to understand this difference for this short period of time because there's a massive difference between holding a molecule to another molecule, making water out of H2O, versus holding H to O to form H2O in the first place. There's a good picture coming up for this. When you hear intermolecular, you have the ability to assume it is hydrogen bonding. So a hydrogen bond is a bond that holds an entire polar molecule, an entire covalent molecule to an entire other one. Generally, for your purposes, just water is going to be what you're thinking about. These questions are really good questions to test your knowledge of all this. I want you to have these for practice, but let me glance across it real quick because I'm not going to make, actually, I probably am going to make a key to this, but just in case I don't have a key sitting in front of you, I believe all these answers have the same letter. Hold on. And you're welcome to pause now and fill out these questions or do them later. I'm just going to read through very quickly on my own to see if I can give you a key easily. So all of these are A. So if you're not going to fill them out right now, just ignore that for now. Write it somewhere else so it doesn't ruin the questions for you. Those are all going to be A. You don't need a key for those. Very important, this second question. Somehow I wound up in a rant without actually covering the most important part of the rant. When we talked about vaporization, the question I was trying to set you up for is this one. What is an example of a chemical reaction involving water? You would think if you saw this question, and many of my students in the past before they met me have had this problem, you would think this answer was anything but what it is. Water boiling is a chemical reaction. The part that would throw you off is the reaction part, because we talked about it being a chemical change. Chemical change and chemical reaction in this instance can be used interchangeably. So an example of a chemical reaction that involves water is simply water boiling at or above 100 degrees Celsius. That's forcing a chemical change. Dissolving sugar, believe it or not, is physical. The sugar can be taken back out and turned back into crystalline. I know that sounds crazy and you think I'm crazy for saying that that's possible. If you evaporate every molecule of water back out after you mix sugar and water and you dissolve the sugar, you will actually have sugar after you evaporate all the water. Water and metal interact. The big problem with that answer is something I want you to be very aware of in many, many areas. Interact is a broad term. You would never want to say something that broad or that simple to describe something that is specific. Water and metal interacting could mean 2 million different things. Some of them would be physical interaction. Some of them would be chemical. Don't allow this to force some kind of mental image for you that creates the thought that it's chemical. What I mean is a lot of people here picture rusting. They picture how water will make contact with metal and then dry, and eventually it will rust the metal. That is most definitely a chemical reaction, but there is no way to assume that that's what that meant because that answer is very, very broad. The other questions you can do on your own. Properties of water, we've talked a lot about this by accident on our way by, so I'm going to make this very quick and simple. You will be expected to be able to say, why is water so important? Why is it the universal solvent? Because water is the universal solvent. So this is essentially a couple of pages to help you understand why water is the universal solvent, why it's so crucial for life on Earth, why it's so crucial for the human body. And a lot of this we've kind of talked about because we've been talking about water. Neutral pH is one we haven't talked about. We will be talking about pH in a few minutes. So water is neither acidic or basic, which is very, very important to being universal for a lot of different things. Most of the mixtures in our body do consist of chemicals that are dissolved in water, and our body is 50 to 75% water. So we're looking from two standpoints. We're looking from the standpoint of the water that's on the earth and then the water that's in our body when we're thinking about these properties. Why water is so universal is it's got neutral pH. So that's one. I think I mentioned that again later in the list. It's a polar molecule. Here's why it matters that it's a strongly covalently bonded polar molecule. It has a strong connection to itself and within its molecule. So needless to say, if you have a substance that's universal to all these different things across the earth, it can't be a weak substance. It has to be a substance that's very strongly held together. In this case, the reason it's so strong is it's a polar covalent molecule. We talked about this some. There's not a whole lot that you have to know about this. I didn't want to go super deep into polar and non-polar with you because that's not something you have to know a whole lot about, but you do need to know that a polar, and remember, polar and non-polar are covalent. They have to be covalent to be referred to as either of those. A polar, remember that a covalent bond shares electrons. So rather than one atom giving and another atom taking and then everybody's happy, they share. There are two ways to share electrons, and they are categorized as polar and non-polar. Polar is unequal sharing. Non-polar is equal sharing. We don't see non-polar much. We only really see non-polar with like a carbon holding itself to another carbon, which is more of a precursor molecule to something else. Things that we would speak about, chemicals that are important enough for us to discuss, are usually going to be polar. The way that I remember this probably depends on your context as far as what you've experienced in your life. When you think about the strength of a bond, and maybe even more specifically, when you think about whether a bond remains or dissociates later. So I'm kind of thinking of like people, like a bond between two people. What would make a bond between two people more likely to continue being a bond between two people versus not? Go with me on this. If you think I'm crazy, that's okay. You can laugh and throw this away. The way I've always kind of thought of it is like, when you think of a relationship where everything is completely equal versus a relationship where everything is very unequal. The ones that are sharing unequally have a stronger connection. So for example, a child and a parent is a fabulous example of this. A child is dependent on their parent, depending on their age, for a lot of different things. They can't really just walk out the door because they need all those things that that parent is providing. Where marriages obviously end all the time. And I'm not saying that marriages are usually equal, because I would say most marriages are not equal in one way or another. But it It is more feasible to split from someone if it's all totally 50-50, everything's very equal, everyone does the same number of chores, contributes the same emotional stability to the relationship, contributes the same money to the relationship, whatever you want to think of it as. That's much easier to just drive a line between. So it's a weak bond if it is totally equal. If it's unequal, the way I kind of think of that, again, it depends on your experience, is like if one person is financially dependent on another, like a kid and a parent or a lot of relationships, or they're physically dependent on them to feed them, stuff like that. That is a stronger bond because one person has a lot more control and adhesion in that relationship than the other. Again, if that sounds crazy and you're like, no, I think it'd be easier to split if you are polar, I don't know. That's the only way I've ever thought to relate it to life. If that doesn't make sense to you, hopefully it just makes sense to you to remember polar being unequal and then non-polar being equal. Specifically, what I mean is in a polar covalent bond, the same number of electrons are being brought to the bond by each part of the bond. So that would be like carbon's sharing 2 of its electrons, oxygen is sharing 2 of its electrons. Polar would be oxygen is sharing 4 electrons, carbon is only sharing 1. So in a chemical sense, that is a much stronger bond because it is much harder for the two to dissociate from each other, especially the one that's getting a lot of electrons from the bond. So that's like property 2. It's strongly covalently bonded, it's polar, and that makes it a very strong molecule that's very hard to dissociate. They could ask anything kind of generically speaking about that. They could say, you could see a lot of questions that are like, what makes water the universal solvent? You could see answer choices that list all kinds of different things. You could see a bunch of things that don't have anything to do with water, and then a random thing that is from this list, and there's no telling whether that would be the fact it's polar, the fact it's strongly covalently bonded, the fact it's neutral in pH. So you just kind of have to have all these properties loosely memorized, but again, they all make sense. When you think about water and its usage and why it would work in so many ways as it does, hopefully a lot of these make sense and they're natural. You could not be universal to a lot of different things if you were super acidic or basic. If it was easy to break a molecule apart, it wouldn't make as good of a molecule. This is a little bit more specifically what the bond is. You are unlikely to need this, but if you like to be really, really prepared, you're good at memorizing, or you're trying to score ridiculously high, it might not hurt to know what these numbers are just in case. Water molecules are attracted to each other like magnets with hydrogen bonds. That is a different ordeal than the polar molecule. So the polar molecule, and this is a good illustration, is referring to how H2O becomes H2O in the first place. So that's the intramolecular force that's creating H2O. What they're showing here is the hydrogen bond that is holding this H2O to that H2O, and the hydrogen bond right here that's holding this H2O to that one. Both of those are important properties. Both of those are very distinguishing properties for water, and both of them have to do with why water is such a successful solvent. So there's the polar bond between the hydrogens and the oxygen making H2O, and there's the fact that they engage with each other. Each H2O engages with any other neighboring H2O using hydrogen bonds. Those are both important. So I guess we'll say this is part 2B, perhaps. So that's 2A. However you want to think of these is totally fine. If you want to just circle the key parts, that's also probably good. Thermal stability, which you can see I've got divided up into a couple of other more specific points. Extreme temperature resistance is very important because if you think about a universal molecule, if it was easy to freeze or melt or vaporize a molecule, it would be much harder for that molecule to be universal than if it has thermal stability. Extreme temperatures are required for phase changes. It can't get a little warm and the water evaporates. It requires a huge change, and that's relative to other substances. So we're comparing water to a million other possible liquid substances that are not universal. These are some of the reasons that they wouldn't be. So like ammonia has a super low boiling point. You can boil ammonia with the stove on low. So if that was in the oceans, you would have way too much water evaporating and vaporizing off the earth, and the earth would dry up. There's three things that I say are true about the thermal stability for water. So this would be point number 3. High specific heat means that it takes a lot of heat for a long time. So there's 2 parts to that. To change the temperature of water, and certainly to vaporize it, requires a lot of heat for quite a while relative to other substances. This is important. High specific heat is important because it keeps the human body from getting too hot. If the water in your body was changing temperatures with the environment around it, you'd be in big trouble. And it's important to large bodies of water evaporating appropriately rather than just totally evaporating and everything is just gone because it got a little warm. High heat of vaporization, you know from what we've been doing that that's specific to boiling. It takes a lot of heat to vaporize or to boil. Low freezing point takes a very cold temperature to freeze, which is important for exactly the same reasons on the opposite end of the spectrum. Solvency would be the 4th key property. That's the ability to dissolve other chemicals. That's probably one of the most important, even as important as these all are. Water is the universal solvent, right? And this says solvency. So a solvent is a substance that things dissolve into. Water's ability to dissolve all kinds of different things, dissociate all kinds of different molecules, is very, very important. It's a primary reason why our body can move substances through different systems, is because you just dissolve the substance into water and send it around the body. Cohesion and adhesion, I'm going to call these 5A, 5B because it's good to think of them together. Cohesion is the tendency of molecules within a substance to cling together. This, I am very much talking about hydrogen bonds. Adhesion is the tendency of one substance to cling to another. So cohesion is H2O clinging to all other H2Os that are within its proximity. Adhesion would be water adhering to the body's tissues, forming things like membranes. So water sticking to things around it is very crucial to the way our body works. Water sticking to itself, to other molecules like it, is critical for everything that water is crucial in. And then chemical reactivity is kind of like solvency. They are 2 different things. That's the ability of water to precipitate in chemical reactions. So not only does water ionize chemicals like acid and salt, but also particles that are released from reactions. You don't need to memorize the crazy details that are in there. Just know chemical reactivity is important. That it can dissociate molecules, and it has a relationship to pH. Hopefully this and this you recognize as being things that you learn about with pH, which we're about to do. So those are your properties of water. Again, don't have them memorized, just have a logical base for what they are and why they are what they are. All of these things are easy to remember if you've taken the time to form the right mental images of them. And that's all you really need to do probably to remember them enough to recognize them on the test. Energy is a very quick little side step. I just want to mention a little bit about energy. The questions that you would get for energy will be relatively straightforward. You'll just be given kind of a scenario and you'll answer what type of energy it is. First of all, the 2 big categories, and you might want to elaborate your notes here, are potential and kinetic. So every kind of energy that you could possibly be asked about fits one of these 2 categories. Potential energy is stored energy. and kinetic is energy of motion. So those are kind of opposites. Potential energy is stored. It would turn into kinetic energy. Kinetic energy is energy that is in motion. There are subcategories that go with each of these. Usually what you're going to see, you're just going to need to be able to say whether it's potential or kinetic. A couple of important categories. One of the categories of potential is chemical. Chemical energy is very much us. It's what our body does. So like C6H12O6, otherwise known as glucose, that is potential energy. There is a whole bunch of energy that is housed in these bonds. What does our body do with glucose? It dissociates all of those bonds, and that releases energy. So the kinetic energy for our body, energy that's in motion, energy that's currently being expended, would be the result of breaking these down. That's the only type of potential energy that is important to you. There's several kinds of kinetic. Most of them will be relatively obvious if you do actually see specifics and you have to be more specific. One of them is thermal. So remember, all of these are energies of motion. Thermal would be heat energy. So one way you can produce or use or put into motion energy is thermal with heat. There's electrical. You may remember from other places that I've told you electrical is the movement of electrons. The same movement of electrons generates energy in our body as causes a light to turn on when you flip the light switch. That's all electrons traveling down a gradient that causes that. And then the other one that's important, there are others, but these are the ones that you would actually possibly see, is mechanical. And that is motion, which kinetic is energy of motion. But mechanical is like one thing pushing against another, creating actual motion. So mechanical is like the brake and gas pedal in a car, the way your foot pedals a bike. Those would be mechanical, when one thing contacts another and pushes with the energy that's in it. So that's basically it on energy. You really don't need to know a whole lot. There's a couple pictures here. If you want to look up more pictures, certainly do. Potential energy versus kinetic in the sense of firing a bow and arrow. So potential energy would be when you've got it pulled all the way back. It's completely charged. You can tell that there is potential energy. You can tell that if you let go, it's definitely going to cause the arrow to go flying. Then kinetic energy would be, if you can see this, it's really hard to see. The arrow has literally been released. His hand is no longer on the bow. So now the arrow is in motion. So you're charging the arrow here, and then the arrow is in motion here. Another example that they have is potential with a hammer being like holding it up in the air. So when you're holding a hammer up in the air, again, there is energy trying to fight against you. You have to hold the hammer up because gravity wants to pull it back down. So you're storing energy in your muscle at that time that's holding the hammer up. Kinetic energy is swinging the hammer down. So once you essentially let go and allow the hammer to fall, it is in kinetic motion. You'll notice there's always a blue arrow with kinetic motion. It's something coming towards something else. The mechanical element can show up in this example because that's when the hammer actually hits the nail. You still have kinetic energy happening in a totally different way when the hammer actually hits the nail. Now you have this still in motion and you have the nail in motion. That's mechanical energy. One other example that I was going to give relates to the body. That's an important one. Actually, let me give one other non-body one first. A really good example is, let's say that you start up your car and you pull out of your driveway and you go to a stop sign and you stop the car. And hopefully you drive an automatic transmission. They don't seem to put so many stick transmissions out anymore. But in an automatic transmission, it's easy to tell that there is potential energy. So when you push the brake, you have to actually push it. And if you're not paying attention and your foot kind of starts to let off the brake, what happens if you have an automatic transmission? The car actually pulls itself forward. So your car is constantly trying to pull itself forward. It constantly has kinetic energy trying to pull it forward in kinetic motion. The brake causes us to change the kinetic energy of the car driving down the road into essentially the brake holding that kinetic energy. So when you press the brake, it is resisting against what the car wants to do. And when you have the brake held, it's bottling up its energy, essentially. So the brake is causing the natural kinetic motion of the car to be stored temporarily. And so there's pressure against the brake. There's mechanical pressure between the transmission of the car that's trying to pull it forward and the brake that's pushed down. So you're in potential energy if the car is running and wants to pull forward, but you're holding the brake so that it can't. And then you're in kinetic motion, whether you're pressing the gas pedal or whether the car is just rolling because the transmission is pulling it forward. Both of those would be kinetic. All of those are examples you could see because this is a chemistry test, not a physiology test. You could also see this cross over with your physiology, though, because our bodies are a constant balance between potential and kinetic energy. So all the molecules that we use as energy, which is essentially glucose, those are potential energy before they've been sent through our cellular respiration cycle. Once they're sent through cellular respiration, they're broken all apart from each other. So you no longer have C6H12O6. And what happens is we take all the energy out of there. So when you bond all these different things together, you're actually creating electrical energy because you have electrons that are moving around, being shared. You're creating more and more and more electrons together when you build a molecule that's this big. All those different electrons have energy. What has to happen for energy to become kinetic is the electrons would need to be flowing. So just like we show here, movement of electrons is electrical kinetic energy. So if this is bonded, those electrons are locked down. They're not doing anything. They're not moving, nothing. Once we break the bonds, the electrons are going to be free and they will flow down a gradient as electrons do. And that will be the kinetic energy of our body. Cell respiration is where this change happens, which is covered in depth in biology. The next page says solutions and mixtures. The rest of this stuff you're going to take pretty lightly. I'm going to go through it fairly quickly because it's not super important. A lot of it is not super important. So one of the critical things you need to know is what is a solution and what is a mixture. I'm actually going to start with mixture because it will make solution a bit easier. So a mixture is exactly what it sounds like. It's exactly what you would say all the time in referring to a mixture. Two or more substances are combined. You wouldn't call something a mixture if it was just one thing, right? So there'd have to be two things. A mixture could be anything from like salt being perfectly dissolved in a uniform manner into some water, or wood, big chunks of wood put in concrete. So there's no difference from one end of the spectrum to the other when we call it a mixture. So a mixture, all you need to know for that is it's two or more substances combined. More specifically, a very specific type of mixture is a solution. So the wood in concrete would not be able to meet the requirements of a solution, but it would be a mixture. Solution is when a substance or a solute is mixed with a liquid or a solvent. Water is the one we've been talking about all day, and is dissolved into the liquid. A solution is homogeneous and symmetrical. So it doesn't count as a solution unless every drop of that glass that you dissolved that salt into that water in is exactly the same. So if it doesn't mix in a perfectly uniform, symmetrical manner, then it's not a solution. So for example, when you put oil and water in a glass together, if you've ever done that, they don't mix, right? They kind of hang out in their own area. You can see a little bit of water tainting the oil. You can see a little bit of oil tainting the water, but they are certainly not uniform. You can see that there's more oil in one place, more water in another. So this would refer more to, like, a good example for most of you is when someone goes into the hospital and we put them on an IV for hydration. That's normal saline dissolved in water. So the typical IV that's used just for hydration is a perfectly uniform solution of sodium and water. And it's 0.09% sodium related to water. So it's not a whole ton of sodium, but it is perfectly evenly distributed throughout the IV bag. You don't have to mix up the IV bag to achieve that. It stays that way. So that is a solution. The amount of solute, so remember that a solute is the stuff that goes in there. So like sugar, salt, something like that would be the solute. In a solution is the solution's molarity. I just want you to be familiar with the word molarity for two reasons, one of which is still coming up in the notes. So molarity would refer to how much solute to how much solvent. The 0.09 is a percentage number, but that would refer to the molarity of an IV hydration solution. The way that they do it is they put the molecules of solute per liter of solution. So if you had two molecules, they call molecules moles. So if you had two molecules of NaCl, meaning you had NaCl and then NaCl again, here's molecule 1, molecule 2, are dissolved in a 5-liter solution. So remember that the solvent is always in liters. Then your molarity is 2 out of 5 or 0.4. If this were saline, you would end up at 0.9 right here because you had X amount of sodium dissolved in 1 liter of water. IV bags are done as a liter. Moles are coming up in one other place, so we will hit those again in a minute. When I say homogeneous mixture, referring to a solution, homogeneous essentially would mean that every part of the solution is exactly the same. There's only one type of distribution of solute to solvent. So you'll notice under mixture that it says heterogeneous mixtures are those in which the composition and properties are not uniform. The example I gave was wood in concrete. There is absolutely nothing uniform about wood in concrete. So that would be heterogeneous, where salt perfectly dissolved in water to make an IV solution would be homogeneous. The last thing on here is a brief intro to pH, which then expands into better notes about pH in a moment. So pH stands for potential of hydrogen. Whenever you talk about pH, you're going to be talking about solutions. So that's why I take solutions and then I go into pH. So pH would be a measurement of the concentration of hydrogen ions in a substance in terms of the number of moles of H+. So there's the word moles again. H+ is a molecule that they are referring to. And when we do pH, what we're talking about is how many molecules of H plus a particular solution has. A lower pH number indicates a higher concentration of H plus. So a lower pH would be a higher molarity of H plus. A higher pH number is a lower H concentration. So something that is acidic versus basic. Acidic would have a whole bunch of H plus all over the place. Basic would have less H plus, kind of like this. And then the other way that it can be thought of is it would have hydroxide, where the H pluses that are in the solution are being bonded with something else, causing OH minus, which is kind of the molecule you think of with basic. So H plus is something we think of when we see acidic. And then OH minus is something we see when we see basic. You're probably not going to have to deal too much with the actual molecules. The stuff that's on the next page is most likely what you're going to see. Water has a neutral pH, and a neutral pH would be the number 7. Anything with a pH that reads lower than 7 is acidic. So our acid right here would be anywhere from 0 up to, 6.9, almost 7. And then anything with a pH higher than 7 is basic. So that would be from 7 to 14 would be the reading for the pH. Examples, so acidic, urine, stomach acid, citric acid, vinegar, hydrochloric acid, anything that says acid in it, obviously. Basic examples, bleach is very basic, soap, baking soda, ammonia, egg whites, and seawater. So basic chemicals are usually aqueous solutions. Aqueous, I think I've mentioned this in other chemistry, but if not, that's liquid. They have a bitter taste, a soapy or slippery texture, and then if you used litmus paper, it could restore a blue color. Litmus paper is a tool that they quite literally use to measure whether something is acidic or basic. It starts out blue, so litmus paper is blue litmus paper. If you put it in an acid, it would turn red. If you then turned it red, put it back into something that's basic, it would turn it back to blue. The reason it has to be so complicated is if it never turned red, you wouldn't be able to tell that it turned blue. So litmus paper is blue. You would take a litmus paper and put it into the acid first. And if it was, in fact, acidic, that would turn the paper red. If you then take it back and put it back into a basic, it will turn back to blue because it is a basic solution. Acidic chemicals are a unique class of compounds characterized by consistent properties. Most significantly, something you can't really see, which is the H plus atoms. And it can be described as a tendency to dissociate from parent molecules and become charged, which is why it's H plus. Properties are sour taste, changing litmus paper to red, producing salt precipitates in reactions with bases. The stuff that's really chemistry driven, you're not going to have to know about, so you don't need to worry about the salt precipitates or the ionization of H plus or any of that. Definitely have this very basic comparison. I would study these two things together. So bitter taste for basic chemicals, sour taste for acidic, litmus paper red, litmus paper back to blue. Soapy and slippery texture is, if you've ever used bleach for anything, if you ever clean anything with bleach, you would recognize that your hands feel really weird and slippery and soapy when you've used bleach or you've put your hands in a bleach-like solution. So just be able to picture kind of what they look like. Most likely the question you'll get is one of the things coming up that we're going to discuss in a second. Anytime, so this is pH scales. These are two different ones. They're not really different in terms of the factual nature that they are covering. but they look different. They have different types of examples, and then they show the numbers a bit differently. So on both of them, I'm going to circle neutral. One of these I like a lot better than the other. I just want you to have exposure to it. The one on the left is the one that I like from the standpoint of what usually gets asked. So on this one, it shows that a pH of 7, which would be pure water or something like that, would have a concentration of hydrogen ions of 1. If you went down in pH 1 notch, so you went a little acidic to a pH of 6, it would be 10. If you go down to a pH of 5, it's 100, and so on. When you're on the basic end, you have the same progression, except it's 1 over 10, 1 over 100, 1 over 1,000, and so on. Remember what we originally said. So all of this refers to the presence of H+. If you just think about that and you just ignore the fact that OH- would exist in basic solutions, if you just think of H+, something that's extremely acidic, the most acidic thing is battery acid, would have a ton of H+ because it's extremely acidic, and H+ is seen in higher quantities in acidic solutions. If you go way down here, something that's extremely basic will still have a little tiny bit of H+, but very, very little. Not going to have very much at all. It's going to be a teeny tiny fraction decimal that you can barely even interpret. On this picture on the left, here's the question you could get that would seem like a really hard question to answer. They'll say when you go from a pH of, let's say, 7 to a pH of 6, the H+ concentration changes by what? This is something that is going to make sense, but it's also going to be a little bit of a memorization. There's going to be a memorization piece to it. When you go from one pH to another, the change in hydrogen ions is how many times more or less is the way that they ask the question. The numbers on the picture that's on the left do a great job of illustrating this. The ones on the right don't. This one looks at it in scientific notation. So you're getting, as you're moving toward the basic end, you're getting this teeny tiny negative exponent. As you move up here, you're becoming positive in exponent. I don't see many questions that use scientific notation and that use exponent. So you really just need to have a general idea of how that would work. And that's it. I'm going to do that part and then I'm going to go back to the other picture. So if we zoom this in a little bit, what you'll notice is that although it looks very complicated to interpret this picture, it's really not, because, for example, if the pH is 4, then the concentration is going to be 10 to the negative 4. If the pH is 7, it's going to be 10 to the negative 7. If the pH is 14, 10 to the negative 14. All the numbers are negative except the very, very, very most acidic. Also important to note, these two pictures are upside down from each other, if you haven't noticed that. This has acidic at the bottom. The other one has acidic at the top. So what I'm showing you here is just in case you see something weird, either within a question or you get asked a question about something weird that has to do with scientific notation. This is the very simple and easy way that you can line it up with what you already know. So you're going to have a 10 every time. You'll notice every one of these is a 10. Scientific notation is where we say 10 times something to the something. The fact that all these exponents are negative is because we don't have a concentration of 100% or higher. A negative scientific notation makes a number like this. So when you're looking at concentration of something, you would expect, even if it has a very high concentration of hydrogen, it's still going to be a little decimal number. So even the most acidic solutions, they're still mostly water. They just have a lot more H plus added to that water than a basic solution does. So the only place that it's not a negative exponent is at the very, 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 very extreme end. This would be like battery acid. So if they asked you something about this or they mentioned this in a question, all you would need to do is know that they're all 10 to the negative something, and the something that they're 10 to the negative of lines up directly with the pH scale. Going back to the left and zooming back out here. So the question that I want you to be most prepared for besides the general properties is, if I go from a pH of 7 to a pH of 6, I have how many times more hydrogen ions? So it's obvious here, right? Because you were 1, now you're 10. So if I go from a pH 6 to a pH 7, and I'm just going to write these as really simple so that you can get the notes down. From a pH 6 to a pH 7, I've got to multiply my hydrogen number by 10. That takes me from a 1 to a 10. What you'll find is each and every time that you move one digit down the scale, from 7 to 6, from 6 to 5, from 5 to 4, from 4 to 3, and so on. So anytime you make just one movement from one to the next, to the next, to the next, it's always times 10. So each time we climb one digit on our pH scale, we have 10 times more hydrogen than we did before. So pH of 7 versus pH of 6. A pH of 6 has 10 times as much hydrogen ion. pH of 5 has 10 times as much hydrogen as a pH of 6, and so on. The trick to this is being a little familiar with this chart, because you have to be used to which way it moves. So this chart starts at pH 7 of neutral, and that's where they all start. So always in the very middle is neutral. When we go up or down, depending on the chart, we go acidic or basic. We go downward to get there. So if this is pH 7, we go 6, 5, 4, 3, 2, 1, 0. With basic, it's the opposite. We go 7, 8, 9, 10, 11, 12, 13, 14. When they talk about something's pH, when they say the pH of water is 7, the pH of the human body is 6.9, they're talking about this number right here. And that is most of what you're going to need to be familiar with. If you walk away from this class still a little confused on pH, but you know that a pH of 14 is as basic as it gets, and a pH of 0 is as acidic as it gets, and then 7 is neutral, you're probably prepared for almost everything you're going to see about pH. There are harder questions sometimes, and they usually have to do with how many multiples you would climb. So another example of that, I'll go back to our first example. When you go from a pH of 6 to a pH of 5, you have how many times more hydrogen? You have 10 times more. They could also say, what about if you went from a pH of 6 to a pH of 4? So it's very common that there's a number skipped in between. You're traveling 2 places. So if you went from a pH of 6 to a pH of 4, you would go times 10 and times 10 again. When you take something times 10 and times 10 again, another way of saying that is it was times 100. Again, for you to study this and grasp this is not going to be overly difficult because you see the numbers right here. How do you get from this to this? You go from 1 to 100. You must have multiplied 100 times. How do you go from 10 to 10,000? Well, you'd have to multiply 1,000 times to go from 10 to 10,000. So if you know that it's 10 for each movement, and if you know that you just keep multiplying those together, if you're moving multiple different places, then you'll be able to put a number to anything. If that's still totally abstract, look through your chart some more, listen to that part of the lecture again. You very well might grasp it once you kind of get used to some of the more basic stuff. If you never ever feel good about that, the odds of you getting a question on number are not tremendous. I designed this class for everyone who wants anywhere from a 70 to a 100%. So if you are that 100% person, then it's more likely that this could hurt you if you didn't have a great understanding of pH numbers. If you're wanting 80, 85, 90 even, you're probably fine not having the numerical stuff. And that's noted down here as well. The last thing about pH is that human blood contains buffers. So if blood is introduced to an extreme pH environment, really acidic or really basic, it will buffer right away. The reason that I'm saying that is there are sometimes very elaborate questions that say, what would happen if blood was introduced into a solution that had this crazy pH? And so the way you would want to answer that is that it would immediately buffer. So you would not see the blood become acidic. You would see the blood introduced to the environment, and you would immediately see it start to neutralize very, very quickly. Again, that's a super rare question type as well. The types of chemical reactions are on here as sort of an FYI. These connect a lot to things that we've already talked about a little bit. This just allows you in the odd and rare circumstance where they ask you to identify a chemical reaction. These would be the types. Cross off the second one down, which is precipitation. Cross off polymerization. Those are not yet seen on these types of tests. So types of chemical reactions. The first one is electron transfer. We've actually talked a ton about this. This is oxidation and reduction. I don't remember how many times I said those terms when we talked about this, but I do know that we have talked extensively about it. Oxidation would refer to, and both of these are going to happen with ionic bonds where we're giving and taking electrons. Oxidation is when electrons are lost or they're given away. So all those different reactions that we played out in our other chemistry classes where we saw that something had one extra electron, so it gave that electron to someone else, or somebody received electrons from somebody else. Every ionic bond has a giver of electrons and it has a taker of electrons. Oxidation is where electrons are lost. So to be oxidized is to lose electrons. That also means that if you were oxidized, you would become more positive in charge. This relates to stuff we did extensively, so if I'm going too fast with this, after you've gotten a chance to review, play it again, because this will be super simple if you have done all your stuff from the other classes. Reduction is the opposite. Electrons are gained. So to be reduced, if a substance is reduced, it gains electrons. And if you gain electrons, you will have a lower positivity. Not necessarily you'll become negative. Maybe you will, maybe you won't. But you will be less positive or you will be more negative. You will lose digits off the positive charge. Remember, this connects to all kinds of different things. Hopefully you've mastered all of that by now and you're feeling good about all that, but that relates to back to understanding protons, neutrons, and electrons and those three roles in an atom in the first place. So you have to understand that to understand why you could be reduced without becoming negative, or why you might have already been negative before the reduction started. Now you're just way more negative. Those are all things that we built through in different stages of chemistry. Acid-base reactions are when an acid reacts to a base. That's literally all you need to know about that one. Combination reactions occur when pairs of reactants combine to produce a single substance. So these are a couple of examples. These are really easy to recognize when they happen. Carbon plus O2 is CO2. N2 plus 3H2 is 2NH3. So you'll see that it's an individual component and then another individual component, or a molecule and another molecule. And when you see the little arrow that provides the result is all the stuff over here is combined, which is exactly why they're combination reactions. So if all the reactants end up combined and joined, then you have a combination reaction. A decomposition is the opposite of that. So if I start out with a big molecule that combines all the components of smaller molecules, and then after my arrow, I see the individual parts that would have existed beforehand, that would be a decomposition reaction. So both combination and decomposition have one major thing in common, which is that there's not extra things that are appearing or things that are disappearing. It's an obvious combining or dissociating of the components that are already there. And then you have single and double substitution reactions. Again, just the names alone of these are very close to describing exactly what they are. A single substitution is where a reaction involves an element that displaces another one. And what you'll see is that one thing got pushed from another. So like here you have AgNO together. Cu, which is copper, if I'm not mistaken, pushed Ag out of the molecule and pushed it over here. So that was a single substitution. One item moved. So it either moved from a molecule into its own thing or from its own thing into a molecule. Double substitutions are really obvious because this is where both of them do that. So you had 2Kl and then PbNO3. And so over here you have the 2K with the NO, and then you've got the Pb with the L. I'm sorry, that's I. My bad. That's an I. So you had a double replacement. Each component dissociated and gave what it was paired with to the other component and received something from the other pair. The last one I want to add to this is combustion. So combustion is where it's an exothermic burning reaction. Exothermic because obviously if you burn something, it's releasing heat. And this would be where some type of hydrocarbon, meaning hydrogen and carbon, combines with oxygen and forms two byproducts, which are CO2 and water. So that could be something like C2H2, which yields H2O and CO2. It could be CH4. So the requirement is that it's got carbon, hydrogen on this side. And then over here, it's got H2O and CO2. So those are, again, very easy to recognize once you're aware that those are there. The last component of this class is balancing chemical equations. I'm going to go through just a couple of examples, leave all the rest for you guys to practice. So balancing chemical equations is something most of you have run into somewhere. Honestly, most of you probably really dislike it because you didn't learn to do it in an organized way. So the info that you need to know for balancing equations, first of all, for a chemical equation to be a real one that could actually happen in the real world, the two sides, as in the two sides of the arrow, have to have the same quantity of the different elements. You can't have a chemical reaction where hydrogen is spontaneously created or destroyed. So whatever goes into the reaction also must come back out of the reaction. It can come back out in a very different spot, combined with very different things, as we've seen in different examples, but they must be equal. You can't have more nitrogen on the left than on the right. There are two types of numbers that you will see in your equations in the first place. You'll see subscript numbers. That's like I3, H2O, CO2. So these little numbers down at the bottom, that would be a subscript number. That refers to the atom. So it's a quantity of an atom. The other possibility is a regular number, is what you would look at it as, which would be a molecule number. That's going to be like this 6 right here, like this 3 right here. The difference between those two connects to a lot of things we've talked about. There's a big distinction that we make between atoms and when atoms come together versus molecules and when molecules come together. So we've talked about that in a bonding sense. It also exists when we look at numbers. We can either multiply. So all these numbers are multipliers. Every single number that you see in a chemical equation is saying there's 2 of something, 3 of something, 5 of something. So they're always multipliers. But you could have a multiplier that's just referring to one particular atom, or you could have a multiplier that's multiplying every part of an entire molecule. So an atom, if you look at this first example that we're about to do, you've got I3, and then you've got N2, and you've got I2. For each one of these, and this says Ni3. If it is a subscript number, if it's the little number that's spaced down from the other stuff, it's only that one individual atom that is in that quantity. So Ni3, N is not having the 3 applied to it. This is telling you that in this molecule, there are 3 iodines, and presumably there's 1 nitrogen because there is no subscript that's with nitrogen. This is telling you that there are 2 nitrogen, 2 iodine, and so on. Same would exist with molecules that you're very familiar with, that you deal with all the time. CO2, this is saying that there's 2 oxygens, but it is not saying that there's 2 carbons. H2O, the 2 is just saying that there are 2 H's, has nothing to do with the O. Molecule multipliers are regular sized numbers, and they're written the way a regular number would be. So they're sitting up here like this. So 3 CO2 is a good example. Up here we have 6 O2. Down here we have 2 NH3. So each one of these, this number is applied to each part of the molecule that it's with. Sorry, I wrote that 3 wrong. So 3 CO2 is saying we have 3 carbon and we have 3 O2s. And this is what happens when they combine. So I'm going to go backward for 1 second and do some that don't. So let's say we have 2 NH or 4 OH or 5 COH. So on these ones, and these won't look familiar, you won't see any that are quite this simple. This is saying there's 2 nitrogen, 2 hydrogen. This is saying there's 4 oxygen, 4 hydrogen. This one here is saying that there are 5 carbon, 5 oxygen, 5 hydrogen. When both exist in the same setting, the mutual meanings are able to be applied at the same time. So for example, 3CO2. We already have O showing up in a quantity of 2. So if this molecule didn't have the 3 with it and it was CO2, this is saying that there are 2 oxygens and 1 carbon. If we have a multiplier over here, a molecule multiplier, that's going to apply to each. So you're going to have 3C and you're going to have 3O2. Another way of thinking about 3O2 is 2 O's, 2 more O's, 2 more O's. 1, 2, 3 times O2. So how many oxygens is that actually? It's actually 6 oxygens. So in this, you have 3 carbon and you have 6 oxygen because oxygen was already getting multiplied by 2, and now we multiply the 2 together. All you have to do if you do have both numbers is multiply the 2 numbers with each other. So like here, 6O2, 6 times 2 is 12. That's a much simpler way than saying O2, O2, 3 times, 4 times, 5 times, 6 times. Either way, you'll find out that that is 12 atoms of oxygen, 12 individual O's. You'll see a mix and a balance of all these different things, knowing how they all work, and then using an organization strategy that I'm about to give you. Those are the 2 things that will ensure you can easily balance chemical equations. Here's the strategy that I find really helpful. You have to balance, right? So you have to have the same number of everything on one side as you do the other. You might remember that reactants is what we call the stuff on the left of the arrow. Products is what's on the right of the arrow. So what I do to make sure that I stay organized is before I ever start, I list out what the atoms are, and I put them in the same order on each side. Then I can fill in how many nitrogen and how many iodine are on the left of the arrow, how many are on the right. Before I ever start, I can see my numbers compared with each other. So this has 1N, 3I. Over here we have 2 and 2. This allows me to see what I need to change. There's only one thing, well, there's 2 things that are very obvious that I need to change. This is a 2 while that's a 1. This is a 2 while that's a 3. I'm always going to take what I think is going to be the path of least resistance first. So the easiest thing I think is to get this 2 to apply over here. So if I go to the left of the arrow and I want to turn nitrogen into having 2 instead of 1, I'm going to do this. That's the only option here, because if I only have 1 nitrogen and on the other side I have 2 nitrogen, there's nowhere else I can multiply nitrogen. As a side note, I just talked about the 2 types of numbers. We can only do mole numbers. We cannot add subscript numbers. We can't change chemical composition. All we can do is say we need this many molecules of this and this many molecules of that. That's where, if you've ever had trouble with chemical balancing before, that's where your trouble originated, is you mess with one thing and by default you wind up messing with another thing, and then you've got to fix something else because of that. So here, there's only one place on the left that we can mess with nitrogen. We have to get it from 1 to 2. We don't have a choice there. So we have to put that 2 molecule next to Ni3. That fixes this. That puts this at 2 so that it now matches this. What does it do to the I that's on the left? Now you have 2 times I3. 2 times 3 is 6. So now you have 6 iodine instead of 3. That looks like a mess, but it actually helps us out because when we look at the other side, we can now very easily turn this I2 into a 6 by having it multiply by 3. So all I have to do is multiply that by 3. That does not affect any other molecule. It only affects iodine. And now we have 6. So now we have 6 and 6, 2 and 2, and we are balanced. I'll do another easy one so that you can see the writing process one more time, and then I'll mention a couple things, and I will leave you to work on these. So the other one that we'll look at is this one here. So you've got hydrogen and then fluorine on each side. You have 2 and 2 over here. Your arrow is right there. You have 1 and 1. This one's very easy to see how you multiply it, but your process is the same and you don't know it's easy until you've gone through your process. So when we look at hydrogen, we need to get the right-hand side to be a 2 instead of a 1. Same thing with fluorine. Thankfully, in this case, we need to make the exact same change to both molecules, and that's thankfully because they are parked together right here. So if I just put a 2 there, that fixes hydrogen, and it fixes fluorine, and all 4 of them match. So a lot of them will be easy like that. A lot of them are a little trickier, involve maybe more counting. The second one down, I just want to mention this. I want you to work on this. Hopefully you recognize this equation. If you didn't, hopefully it at least looks familiar. That is the photosynthesis equation. If the 2 sides were flip-flopped, it would be the cell respiration equation. Something very important that can save you a lot of time and heartache on your test is if you see photosynthesis or cell respiration, you need to have a 6 everywhere except glucose. So whether it's cell respiration or whether it's photosynthesis, cell respiration looks like this. So it's opposite. You will literally put a 6 in front of every component of the equation except glucose. So if you do recognize, and of course be careful to make sure that it is the photosynthesis equation, not just something that has glucose in it, but if it is the photosynthesis or cell respiration equation, you don't need to balance it. It's actually kind of a pain to balance it. You don't need to if you can identify that it is one of those equations. The last one I'm going to do is going to be this one here. This one is a little more complicated from a counting standpoint, and that's why I'm going to do this one. So on the left-hand side, I have 3 carbon, I have 8 hydrogen, and I have 2 oxygen. When you get to the right, it's a little trickier because you may not initially notice, but you have oxygen in 2 different places. You have to count those up together in order to put your number here because they are on the same side of the arrow as one another. So for the first molecule, you have 3C, and we don't see C anywhere else, so we'll just put a 3 there. And then you have, in this molecule, you have 3 times 2 is 6 oxygen. In this molecule over here, you have 4 H2, and that's the only place we see H. So that's going to be 8. You have a molecule number and an atom number. So you have 8 hydrogen. And then you have another 4 oxygen. You have 6 oxygen here, 3 molecules times 2 each. And then over here you have 4 times oxygen. That means that you have a total of 10 oxygen. Once you get through the process of adding that all up, this actually becomes a very, very, very easy question. If that was too fast, or if you want to try this and make sure that you did it right, you can back me up 15 seconds or however long to just see the count up process again. Once you see that, you'll see that there's only one thing that needs to be adjusted, and that's oxygen. Oxygen so happens to be by itself so that you can mess with it and not anything else, which is why this pans out so well. How do I get from a 10, or from a 2 rather, to a 10? Well, I would need to multiply by 5. remembering there's an atom number of 2 there. So we don't want to put a 10 because then you'll end up with 20 instead of 10. We want to have 5 O2 so that we then have 10 total oxygen. On the next page, I'm going to point out there are some equations on this next page that are largely too difficult for you to need to do them. You can pretty easily recognize them because they'll have parentheses with subscripts. I will show you how one of those breaks down so that if you feel better doing those anyway, even though they might be a little too hard, you know how to do it. So when you have a subscript number like this and it's parked outside of a parenthesis, that kind of works the same way that math normally works when that happens. So in this case, Zn is zinc. This 2 would distribute to both of the things that are in the parenthesis. So this would be ZnO2H2. When you see ones that have these parentheses, start by distributing your subscript to the 2 different places or 3 different places that it needs to go. Then balance your equation. Definitely don't try to balance it before you redistribute. If it's something like these down here, you're definitely not going to see these. When you distribute the 2, just like when you do a molecule number, if there's a subscript on each side, then you're going to multiply the 2 together. So you're going to have Ca3P2O8 in that case. Again, you don't have to do these really hard ones. The odds of you seeing them are very low. If you're trying to do absolutely everything, or if you're good at chemistry and you feel like it's not much of a stretch for you, those 2 will help you. Those 2 examples will help you be able to do those as part of your practice. They will be on the key. And then just make sure that you do that distribution instantly so that you can change it from a foreign-looking equation to one that does not look foreign. So that is it for Chem 3, which means that is it for HESI Chemistry. I would be surprised in most of your cases if you don't have to watch each of these a couple of times. It's a lot of information covered in just a few sets of 2 hours. So if you're going to do any reworking, rewatching, restudying, start up at the beginning again. And hopefully now that you've seen all of this, hopefully you can start to connect a lot of the dots that I loosely connect as we go through, because all these concepts teach into each other. So if you get really good at all the stuff up at the beginning, you'll start recognizing the existence of things that you've already worked on as you're progressing into the deeper levels of chemistry. So from here you have your Chem mock, and that is it for chemistry. So go through, memorize everything that I did say memorize, understand the much more content that I've said understand, go back through any of this that you want to, and then you should see reflected in the Chem mock whether you have all the skills down that you need to have. Once you've done all of that, if you have specific questions, let me know, and I will see you guys later.